Okay. Before we dive into the lesson, let's just look at what we've learned so far. Recall Newton's second law is F equals what? F equals ma. That is on your green sheet. I think it's the third or fourth line down. I can't remember, but it's there somewhere. Make sure you know where it is. You'll probably end up memorizing that one because you'll get sick of looking it up. Example 1 says this: a spacecraft has a mass of 3.25 times 10 to the 4th kilograms. Its engine can exert a thrust force of 7.25 times 10 to the 4th newtons. Ooh, Alex, what's A asking me to find? Yep, acceleration. So I did this. I said, okay, Duick says do that. You feel better. And then I was looking, has this question given me a VI at all? Or a time? Or a distance? I don't think I'm going to be using kinematics last unit. I noticed this, well, first of all, kilograms. What's that a measure of? Newtons. What's that a measure of? I said, okay. I think I'm going to use F equals ma. Alex, how would I get the A by itself? How would I move the M over? Yeah. We'll name that Alex's theorem for the rest of this unit. So Alex's theorem says that acceleration is also force divided by mass. The force is 7.25 times 10 to the 4th newtons. The mass is 3.25 times 10 to the 4th. Right around now, I'd be getting my calculator out, and I'd start to crunch the numbers. If you use your scientific notation button, you won't need brackets on the top or the bottom. If you don't use your scientific notation button, then you will have more than one thing on the top, brackets, and more than one thing on the bottom. I'm going to use my scientific notation button.
Couldn't you just do 7.25 divided by 3.25?
Matt, speak to me, what?
Couldn't you just do 7.25 divided by 3.25?
Yeah, it turns out the 10 to the 4ths in this one will cancel out. And so I would actually not even bother typing them in if I was doing this on my own. But for now, do y'all get 2.23? Okay. Units, it's an acceleration. Yep. Okay. B, suppose the spacecraft maintains this constant acceleration for 45 minutes before turning off the engine, and its initial velocity was 5.6 times 10 to the 3rd. Ooh. Liz, what's B asking me to find? Okay, so now I think I'm going to go back to the last unit, and hopefully you're already noticing there's going to be some overlap between what we've done already and this new unit. You can't just say, oh, I'm going to forget D equals VIT plus a half AT squared. No, 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 they're all still fair game, totally fair game. It looks like VI is 5.6 times 10 to the 3. A is, I'm going to write 2.23, but you know I'm going to use my answer button because it's less typing and more accurate. What don't I like about that 45? It's minutes. So I think, Liz, I actually would have just crossed it out right away. How do I convert minutes to seconds? Times 60. So I would have quickly gone 45 times 60. Now the problem is I just lost my answer button for acceleration, so I will use 2.23, I guess. 2,700 seconds. I don't know. Liz, which equation?
Easiest one.
Probably you've ended up memorizing that one out of laziness. And again, that's the only reason you should memorize stuff, because you get sick of looking it up. VI plus AT. So it's going to be 5.6 times 10 to the 3rd plus 2.23 times 2,700. We're going fairly fast. That's about 11.6 kilometers a second. For those of you who are interested, that's actually, I think, just above escape velocity. So this would get us out of the solar system. I'll write I'll go to 3 sig figs. But if you wrote the whole thing, that's fine. Okay. Front row Parker, what's C asking me to find? Front row Parker, what's C asking me to find? I think we're going to get a displacement. Which equation? I'm not going to relist everything since I got it right here. Now, my brain would say this: no matter what, Jaden, I'm using an answer to find an answer. I'm either going to use the acceleration or I'm going to use the final. So now what I would do is I would take the laziest way. And I think, yeah, D equals VIT plus a half AT squared. You could use VF squared equals VI squared plus 2AD and rewrite it. No matter what, I'm using an answer to find an answer. I'll use the one that has the D by itself already. You could also use D equals VI plus VF over 2 times T. That would work as well. That one's a bit of a pain to type. It's got brackets and stuff. This one I can just plug and chug. It's going to be 5.6 times 10 to the third times 2700 plus 0.5 times 2.23 times 2700. Don't forget the squared. You should be able to type this in one line without having to hit equals along the way.
Whoa.
Just saying.
It's a big one.
We're a spaceship. We're moving.
I'm actually going to use Cyclist here.
I made a typo. 5.6 times 10 to the third VIT plus a half AT squared. I think I'm right. Do you get that?
Yes.
I heard Matt say I'm going to use sig figs. I think you mean I'm going to use scientific notation here. So I'm going to go 2.32
That's fine.
times 10 to the 1, 2, 3, 4, 5, 6, 7, I think, yes?
Oh,
2.32 times 10 to the 7th.
I accidentally did 23.2.
And meters. If you wrote 23.2 times 10 to the 6th, I probably would take a half off because that's not proper scientific notation. Scientific notation, 1 digit followed by the decimal point. Okay. By the way, which way do rockets eject their mass?
Downward.
Downwards or backwards? Which way are they accelerating?
Upward.
So what's pushing them forwards? It's not the engine.
It's the loss of mass.
Okay. Forces come in. Okay. Let's just zoom in on the engine. The engine exerts a force on the mass. What does the mass do? Exerts a forwards force on the engine. It's one of the challenges with our current rocket technology. We have to bring all that mass with us. If you ever see a big rocket, only about 10% is payload. The other 90% is the fuel, the mass that we have to bring with us to eject out the back at an explosive rate to get the force going forwards. Sorry, warp drive technology is currently not supported by science. So there's limits to what we can do with our current level of space technology. D, what will the velocity of the spacecraft be after 90 minutes? Or after 60 days? Here you go, Ronan, that's something for you. Or after 4 years? Why do you know the answer already without doing any math?
You already calculated 45 minutes.
And 45 times 2 is 9.
No. I agree with Parker, I disagree with Matt. What did I underline in part B?
Turning off the engine.
Okay, so if you turn off the engine in outer space, then what happens?
You keep going fast.
You don't come to a stop. This is why we respect Isaac Newton so much. He was able to visualize outer space at a time when we didn't know much about outer space. In outer space, when you shut your engine off, you're going to keep going in a straight line at a steady speed. Our Voyager probes have both left the solar system. All we did was we gave them a big enough boost to leave the solar system, and then they've coasted the rest of the way. And they will keep going unless they run into, like billions of years from now, the gravitational field of another star or planet way out there. But otherwise, they'll get to the edge of the universe. And there's a pretty good chance they will, because empty space is mostly empty space. They're going to keep going. So what will the velocity be after 90 minutes or 60 days or 4 years? It will be 11,600 meters per second. It's going to keep going in a straight line at a steady speed. What law did we use to come to that conclusion? Do you happen to remember which of Newton's laws that is?
First law?
That's Newton's first. If you want to, you can write down Newton's first. You do not need to memorize which one is which if you just paraphrase them. In other words, if I ask you a question and I said, how do you know? And you said, forces are balanced, so we're going to keep going in a straight line at steady speed. We're not going to accelerate. I'll give you that. You don't need to. But if you say Newton's first, you can drop the mic and walk off, and I'll live with that. But if you meant Newton's first and you say Newton's third, I won't give you credit for that. So it's up to you whether you want to memorize which one is which. Somebody had a question. Yes?
Does that mean, like, if there's a spaceship out there,
Yeah.
is it giving them gravitational pull?
No. If you're far enough away from the gravitational field of planets and stars, then you would not be feeling any gravity. In fact, we're going to talk later on this unit about what we call apparent weightlessness, which is what these space station astronauts feel, and true weightlessness. True weightlessness is you're in the center of the universe and there's no gravitational fields around you. That's what we mean by true weightlessness. But then there's apparent or fake weightlessness. We'll talk about that, but not today. That was a bit of review. Now let's get to today's lesson. Oh, I didn't give Ronan the handout, did I? Free body diagrams. I tend to abbreviate, and so you'll often hear me talk about an FBD. What's a free body diagram? It's a picture that represents the object that you're analyzing with a dot. Any forces that are acting on it are represented with arrows, roughly to scale. What do I mean by roughly to scale? If you know one force is larger, draw the arrow bigger. If you know two forces are the same size, draw the arrows the same size. Roughly to scale. And we're going to use Newton's laws to figure out what forces are acting on the object. So here's 4 free body diagrams, although usually instead of a square, I'll just put a dot in the middle. I'm too lazy to do that. It says the magnitudes of a few forces are not known, but we do know the net force. Analyze each situation and determine the magnitude of the unknown forces. Let's zoom into this first one. So, Sarah, what's the net force in this question? What does it say? 0. So here's my question. If the net force is 0, how big must force A be? Has to be 50. Why? If the net force is 0, that means all the forces must be, I'm looking for a word that begins letter B, balanced. So if I got 50 right, I better have 50 left. Sarah, what must force B be? Has to be 200. But Amrit, now we're going to kick it up a notch. Amrit, what's the net force in this second diagram? Magnitude and direction. 900 up. So how big must C be if when I combine that, I get 900 up? Don't write this down. Is that correct? That would be a net force of 500 up. Right? Does that give you the same as 900 up? Yes. See where we're going with this? Okay. Camille, what's the net force in this third diagram, magnitude and direction? What have they told me? Okay, so for 60 left, first of all, what does D have to be? I want 60 to the left. So what does D have to be? See it? What do you think? 20? Is that okay? Yeah. Ooh, what does E have to be? Okay. Has to be 300. Since there was no up-down force, that must mean they canceled out. Yeah. I'm fussy on units, so yes, it's at your final answer. Units always on your final answer. Okay. I don't make you show units in your middle steps. Some profs do. Not my thing. But final answer, yes. Ooh. What's the net force here, Parker, middle row? Yeah.
30 newtons, right. So it'd be 50 on G.
Okay, now I'm going to say, hang on, let me write this out. Keep going.
Are we able to put 0 newtons for F and H?
First of all, how big must F be compared to H?
There.
There.
Wow.
And we're going to start to generalize, Jaden, and we're going to start to do less with numbers and more with here's a one-size-fits-all scenario. Okay?
That's pretty cool.
Example 3. Now we're going to draw our own free body diagram from scratch. It says this. A book is at rest on a tabletop. You know what? All of your binders. A free body diagram for this situation looks like the following. Draw a little dot. That's the book. I'm going to be very meticulous. I'm going to try and teach you a specific order. So what are the forces acting on your book? Get the obvious one, the one that's holding us all on Earth. It starts with letter G. So my abbrev for gravity, first arrow pointing down, we agree gravity's pulling you down. My abbrev for gravity, capital F, and then lowercase g, force of gravity. Now look at your binders. Are they sinking into the table like quicksand? Are they flying into the air like Superman? Are they accelerating? Then forces must be, I'm looking for a word that starts with letter B. That diagram can't be correct then. That has to be wrong. It is not balanced. What must I draw? An arrow pointing which way?
Up.
Bigger or smaller or the same size as gravity?
Equal.
So what we just put? F table.
We're going to give that a special name later, but for now, sure, table.
Why would it be force equal to force of gravity?
They're the same size. If you want me to write an equation, I would say, Fg equals F table, and if I knew how to calculate one, I could calculate the other. And we'll get there. We're just not there yet. Okay? Example 2, draw a free body diagram for the following masses hanging from a rope. So there's 2 examples here. The first one is at rest. I'm going to represent the mass with a dot right there. What are the forces acting on it? Get the obvious one. Gravity. Which way? Okay, so let's draw an arrow pointing down. Gravity. Is this 12 kilogram mass accelerating down?
No.
Is it accelerating up?
No.
What is the acceleration as a number exactly?
0.
That must mean the forces must be, I'm looking for a word that starts with letter B. So this diagram cannot be right. What must I draw? Is that arrow that I'm going to draw pointing up bigger, smaller, or the same size as FG?
Same.
It has to be there. We call the force from a rope tension. And so I'm going to call that F with a subscripted of T for tension. Okay. Let's look at this second situation. It says now we're accelerating up. What are the forces acting on it? Get the obvious one. Which way?
This is
If we're accelerating upwards, which way must there be a bigger arrow pointing? Upwards. I'll exaggerate it so make it obvious. What force is that? That is also tension. Which of those two situations has a larger tension? The one on the left or the one on the right?
One on the right.
Which of those is more likely to break the rope?
One on the right.
When are you more likely to break a rope? When you're yanking up on it, which is kind of Captain Obvious, I realize, but there's the physics of why that's the case. And I always like it when stuff that I know matches the physics that I'm learning. So you'll hear me every so often say, I know this is Captain Obvious, but it explains why that is. Next page. Some types of forces. One of the forces that you're most acquainted with is the force of gravity. This is the force that the Earth exerts on you. The force of gravity is calculated as follows. Don't write this down, look up. Don't write this down, look up. F equals what?
MA.
Don't write this down.
Lot.
I'm going to use a special letter for the acceleration due to gravity.
Is it G?
Write that down. Hey, is that on your formula sheet?
Yeah.
Find it.
Found it.
Okay.
Weight equals F, G equals F.
Oh, stop. What's another word for the force of gravity that starts with the letter W?
Wait.
And I'm going to be very, very, very fussy. Weight is a force, not a mass. Weight is measured in newtons, not in kilograms. Those are two different things. Mass and weight are not the same thing in physics. They're very different. Example 3 says this. Find the weight of a 35 kilogram object A on the Earth or B on the moon. Since we're doing two questions, I'll put a little line in the middle and I'll do A there and B there. Braden, what's this question asking me to find? Find the weight. No, now. Wait. No, now. Wait. No. Joke. The weight is the force of gravity. It wants me to find mg. Except I'm going to use G Earth in part A, and I'm going to use G Moon in part B. Braden, what's the mass in this question? What's G on the Earth? You've probably memorized this. We're not going to include the negative because we're just finding a magnitude right now, but it's 9.8. What is 35 times 9.8? I could probably do this in my head. It's going to be 350. Take away 343. Double check me.
340.
Yeah. That's how hard the Earth is pulling down on this mass. If we beam that mass to the moon, its mass does not change. What's its mass still, Braden, my friend? But what's the acceleration due to gravity on the moon? I told you in part B, if you read carefully. Which is what? I can do that in my head. It's going to be 35 plus 21. It's going to be 35 and 21, 56. Is that right? This is why astronauts felt lighter on the moon, not because their mass changed, because their weight changed. Their spacesuits didn't get less mass, did not get less inertia. They got less gravitational force. And that's why the spacesuits on the Earth would have had a weight, if we use the imperial system in pounds, of about 300 pounds. On the moon, they had a weight of about 50 pounds, and they were able to wear those spacesuits on the moon. Wearing them on the Earth was bulky and awkward. If you talk to the astronauts when they were training, they were not fun to train in on the Earth because you were packing a lot of weight. But on the moon, not a problem. Your mass, an object's mass, stays the same anywhere in the universe, even near a black hole. What changes based on planet to planet or star to star or near a black hole is not your mass, but your weight. Okay? Very different concept. Yeah.
Why don't they just make the spacesuits heavy enough that when they're in the rocket, they go up, and then once they get out of it, it feels the same as on the moon.
What they did, so you're asking why can't they build a spacesuit lighter, or are you asking?
Heavier. So it's like it feels the same on the moon.
Oh, you wouldn't want that. You want it to be the spacesuits are terrible. Spacesuits, if you talk, Chris Hadfield, for example, Canadian astronaut, he'll tell you after his first spacewalk, and most astronauts will tell you this, you are wiped like you've just played 5 straight hours of nonstop contact football. Once he got back to the space shuttle, once they took the spacesuit off, he said he curled into a fetal ball and floated for about 20 minutes, just shivering and shaking, because everything is so much more difficult. Any hand motion, any movement, there is a massive force resisting you, because you got to remember, you're in a very, very strong balloon that basically wants your arms to go straight out and stay pressurized. So every movement that you're doing, you're having to constantly exert a pretty big force against it, even just to hold your arms still. Spacesuit technology is in its infancy. I hope we get better spacesuits, but they're not fun to wear. Here's the key idea. You ready? To solve situations using forces, Liam, we're going to use a tug of war analogy. We're going to draw a free body diagram labeling our forces. And then we're going to use our knowledge of physics to decide which force is the winning or strongest force, which way we're accelerating. And then we're going to use the following equation. Winner minus loser equals F net. Where F net is equal to MA. So really what we're going to do is we're going to go winner minus loser equals MA. This is our one-size-fits-all equation. I can't give you every equation we're going to come up with. There's going to be hundreds of them. What I can say is this template will allow us to figure out every equation. Let's do a couple here. Example 4. Suppose the box is resting on ice, so we can ignore friction, and the following forces are acting on it. See the picture? A says add any forces you think are missing, and then B says how fast will it accelerate. So there's the ice right there. Don't draw the ground in, just use your imagination. What are the forces acting on it? Get the obvious one.
Gravity.
Okay, so we would definitely still have gravity. You know what? Wait, look up. I have a habit, instead of writing FG, I'll often just write the equation for the force of gravity, which is mg, because that way I've already brought the equation in for bear. So there's the equation for weight. Is this mass sinking into the ice like quicksand?
No.
Is it flying off of the ice like Superman?
No.
So in the vertical direction, the forces must be, I'm looking for a word that starts with letter B. So I'm going to draw an arrow, I'll eyeball it, about the same size as gravity, and that's the ice pushing back up on gravity pulling it down. It has to be there, otherwise it would have to be accelerating. And then we have the two forces, the 14 and the 6. In the vertical direction, are we balanced? So in the vertical direction, no acceleration. But there is my part A. Part B wants me to find the acceleration. Okay. Who's winning? Which way are we going to, which way must we accelerate? So who's winning? Winner. Minus. Who's losing?
6.
And equal.
What does that equal?
Oh my goodness.
MA.
It equals MA.
Alex, how do I get the A by itself? How do I move the M over? This is Alex's theorem. We're going to divide by M. So if you want to right now, you could go cross the M out, big fraction line, and tuck the M there. If you want to on this line, I'm okay with that. And now we're going to plug in numbers. 14 minus 6 divided by, Alex, what is the mass? 3. What do you get? I can do this in my head. 14 take away 6 is 8 divided by 3. It's going to be 2.6 repeating, but double check me.
Yeah.
Oh, is this a fraction? Is there more than one thing on the top? You either have to put brackets around the top, or you might have gone 14 minus 6 is 8. But for more complicated ones, we will absolutely have brackets around the top. They're going to get way more complicated than this, but it's going to be the same procedure. Who's winning? Who's losing? Winner minus loser equals MA. Okay. Example 5. Suppose the box below is sitting on a table and accelerating to the left at 3.2 meters per second squared. A says, add any forces that you think are missing. What are the forces acting on this? Get the obvious one. What else? Are we sinking into the table like quicksand?
No, we're not.
Are we flying off the table like Superman?
No.
So vertically, the forces must be, I'm looking for where that starts, the letter B. You're starting to see why Newton's first law is such a handy law. It really lets us reason out a bunch of stuff. So I know the table must be pushing up with the same force as gravity. I don't think there's any other missing forces. Now, what does B want me to find? Matt, what does B want me to find?
B wants you to find how hard Abe is close.
I'll use FA for Abe and FB for Bill. Okay. Which way are we accelerating? Look at the picture.
To the right.
Look carefully at the picture.
To the left.
How do you know to the left?
It's bigger.
Whoa.
How do you know to the left?
Oh, it's another arrow.
Whoa.
So you ready? Let's try again. Which way are we accelerating?
Left.
Who's winning? Same direction. So winner.
A.
Matt, who's the loser?
Really?
You didn't see. I said, who's the loser? And he looked at Parker. Oh, Parker, Bonson Park, 3 o'clock. If I'm not there, you just start without me. Fine, Matt. Who's the losing force? Billy.
Really?
What does winner minus loser always equal?
MA.
Now, in the question we just did, we used Alex's theorem to find A. Here, they're giving us A and asking us to find a missing force. And that will be the trend. I'll either give you all the forces and say find the acceleration, or I'll give you the acceleration, missing a force, find the mystery force. How would I get the FA by itself?
Plus FB to the other side.
Look at that. I don't need to memorize a new equation. I can derive it. So you're telling me that the force of Abe is going to be MA plus FB. I agree. Take it home, Matt. What's M?
What's M?
Yep.
I don't know.
Look at the picture. No excuses. Look at the picture, okay? It will always be there somewhere. What's A? Look at the picture.
A is 3.2.
Plus, what's FB?
FB is 224.
Yep. That's how big the force of A must be. What do you get?
Really? I don't.
Right? We're going to abbreviate, Parker. Typically using first letters. What do you get, first of all? 40? I'll put a dot to go to 2 sig figs, or I'll even go 40.0 newtons. Question, Matt.
How do you know Abe is winning when it's going down?
It's not going down. It's accelerating to the left.
Oh, I thought. Oh, yeah, I was reading your red arrow. That was so.
No, those are balanced. Vertically, I can ignore them. They're balanced.
No, I know.
Okay?
Ah,
That makes so much
Mr.
sense.
Dewey.
Yeah.
I understand what you did there,
Yep.
but what I'm not understanding is if F equals M over A, couldn't
No, F doesn't equal M over A. F equals MA.
M A? Oh, yeah. So we can go.
Okay, let's do a few more.
You see they pop.
Why?
I like example 6. I like example 6. Example 6 is a nice question.
Must be on a test.
Okay?
I know.
Yeah.
Yesterday when we were taking the test, he said something like that, and I saw that question on the test.
Oh, really? Okay. Darman, what's example 6 wanting me to find? Like you're feeling right now? A little tension? Okay. This is a job for a free body diagram. Now, how do I know I need to draw a free body diagram? What is this question asking me to find?
The tension in the rope.
Okay, that's one force. Is there another force in this question? Get the obvious one. If there's more than one force in the question, almost always you want to draw a free body diagram. So I'm going to represent the mass with a dot. Darman, what are the forces acting on this 12 kilogram mass? Get the obvious one. Which way? I'll write mg, the actual equation. Which way is this mass accelerating? Which way must I have a bigger unbalanced force pointing? Same answer. What force is that? It's the rope. That's tension. So sometimes I use Ft, or if you really want to be lazy, you can just use a capital T for tension. I'll know what you mean. Save us a letter. Okay? Who's winning? Who's losing? Mg. What does winner minus loser always equal? There's our equation. So you ready? Winner minus loser equals Ma. Yep.
I have a question for the last.
Yep.
If you might be a stroke of luck, but if you go m times a, so 5 times 3.2
Yep.
equals 16. If you add it to Billy, that equals 40. Does that work?
That's what we did. It works in this situation based on how I set up the forces, but we're going to get more complicated. Okay? You're doing okay.
No, I'm a bit slow up there.
It's okay. Guys, stay with me. Darman, what are we trying to find? How would I get the T by itself? Okay, do you hear that? To get the T by itself, I would plus the mg over. If you want to, you can draw a little arrow. If you don't, I'll clue in what you did. It looks like for this situation, tension equals ma plus mg. Darman, what's m? The question told us somewhere. 12? What's a? Plus, what's m? What's g? We don't put in this unit, we're not going to put in a negative 9.8. We took care of our negatives and positives with our winner minus loser setup. That took care of all the signs. So g is just going to be 9.8. Which is what? I might be able to do this in my head. It's going to be 12 times 11.8. 12 times 11 is going to be 132. 12 times 0.8 is going to be 132, 96. 132 times 9 points. 141.6?
Yeah.
I'm getting it.
It's the same thing as last.
Okay. If you said 142, that's fine. But I'd like to show off that I got 4 sig figs with decimals in my head. Okay? Parker, you and I are going to do the next one together.
Yeah.
Okay?
Okay, 1 second.
Ready?
1 second. I'm just finishing the last one.
You're ready, Parker.
Okay.
You're ready.
I know I'm ready. I'm just making sure the last one. Yeah. I got it.
Okay?
Okay. So
Example 7. First of all, Parker, what does example 7 want me to find?
the tension on
Like
the
you're
right.
feeling right now, a little tension. This is a job for a free body diagram. So let's put a little dot right there. What are the forces acting on this mass? Get the obvious one. And I'm going to be fussy. I always encourage you. Kids always want to rush to the tricky one that they don't know. If you go systematically, you'll often find the tricky one becomes obvious by the time you get there. So don't rush into, I want your tension first. No. Get the obvious one. What did you say?
Gravity.
Yeah. Force, Abe, force, Billy. I abbreviated. It's a force. I could have written the word Abe and Billy, but why not F for force and then A for Abe, B for Billy? Good question. Okay. Is there a rope in this question?
Yeah.
So there is tension. Now here's my question. Is tension bigger, smaller, or the same size as mg? And how do I know? We've got to be fussy, not because it's pointing down, because we're accelerating down. I know that the force up has to be smaller. I'll really exaggerate it so it stands out. And I'll call that force T for tension. And again, my template is winner minus loser equals MA. Parker, who's winning?
Gravity.
MG minus, who's the loser? Look at Matt. Oh, no, sorry, what? Tension. What does that equal?
MA.
Okay. This one is going to show up an awful lot, so you want to look up. Parker, what do we want to get by itself? What's right in front of the T that I don't like? Immediately in front of it. Immediately in front of it.
Negative.
Yeah. So I'm going to do two things at once. I'm going to plus the tension to that side because now it's positive. At the same time, if you want to, you can put a plus sign there. At the same time, I'm going to minus the MA to that side. I'm going to get this. MG minus MA equals tension. It sort of looks like the MA and the tension swapped places. A couple of years ago, my students nicknamed this the swappy dance, they called it. So I did the little swappy dance. I've got the T by itself, and so now I can plug and chug. What's M?
12.
What's G? 9.8. I don't need to put the negative in. I took care of the negative with my winner minus loser setup.
12 and then 4.2.
Yep. Which is what? Do that one in your head, Mr. Dick. Well, maybe. 12 times 5.6 is going to be 60 plus. 67.2?
Yeah.
Yeah.
There you go.
Nailed it.
It's a force, so newtons. Okay? This idea, Jaden, of a free body diagram, who's winning, who's losing, equals MA, you won't learn anything new in Physics 12. This is one of the most useful, in your Swiss Army knife of physics tools, this is one of the most useful tools I can give you, a free body diagram. Example 8. Example 8. Ronan, what does example 8 want me to find? Is there also another force in this question? Gravity? This is a job. Is there more than one force? This is a job for a free body diagram. Ronan, what are the forces acting on this rope? Get the obvious one.
Gravity,
Which way?
downwards,
What else?
and acceleration,
Acceleration's not a force. We don't say that.
tension,
Tension? Which way?
upward,
Okay. Bigger, smaller, or the same size as mg? And how do I know?
bigger, because it's moving up.
Why is Ronan wrong?
Because
It's accelerating.
Is it?
Yeah.
Is it?
Oh, no, it's not.
it's moving.
What two words should I have underlined that should have been a ding, 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 ding? Pay attention and notice it. What? Everybody underline that right there. If we're at a constant speed, what's A as a number exactly? Let's make a little note here. And if A is 0, the forces must be, I'm looking for a word that starts with letter.
Ronan's wrong.
I think we were all wrong.
Ronan's the loser.
Now, here's the beauty, okay? If you missed that, but you're still careful, you'd probably get it right. And I'll show you how in just a second. But because they're balanced, that means it's a tie. It's like elementary school sports day. Everyone's a winner. It's a tie, okay? So my equation for it's a tie would be this. Tension equals mg. Now, write that down and then look up. What if, like Ronan, you saw the word up and you confused moving with accelerating? And that happens all the time. Don't feel bad. Okay, you would have then said, well, tension must be winning. You would have said minus mg equals ma. How would you get the t by itself? You would have done this. And then, as there's a reason why I've harped on units. You would have said, what's the mass? What is the mass? What's the acceleration? Can that be an acceleration? How do you know that can't be an acceleration?
The square.
And I hope you would say, wait a minute, something weird's going on here. I don't see an acceleration in here. And you would say, constant speed. The only way you'll get this wrong is if you panic and stick a velocity in as an acceleration. And if you do that, I'm sorry, you deserve to get it wrong because I've taught you better. I have hammered units from day one, partly because I knew this was coming down the pipe. And so you would say, oh, and notice what we get. The same equation that if we spotted the tie in the first place. So as long as you're careful with units, you'll be okay. Ask your question, Ronan. Ronan, ask your question.
How are the forces equal since going down?
It's not accelerating. All Newton's laws tell us is which way we're accelerating. They tell us nothing about which way we're moving. They only tell us which way we're accelerating. Are we accelerating?
No.
Then forces must be balanced. Okay?
Yes. So don't worry about the one.
But I like this question. I like this question. I like this question. And not only that, I'll almost always give you the velocity as a number just to tempt you to put it in for the acceleration, even though the units don't match.
You're just trying to be a sneaky guy.
No, I want to emphasize, don't confuse acceleration with velocity. Newton's laws don't tell us velocity. They tell us acceleration. Ronan, what's M?
12 milligrams,
What's G?
9.8.
Don't need the negative in this unit because I took care of that with my winner minus loser, which is what? I can do that in my head. It's going to be 120 take away 2.4. No, 120 take away. Yeah, 117.6.
Yeah.
Okay. I like example 9. I like example 9. I like example 9. Hey, Jaden, what's example 9 asking me to find? So looking at this, do you see a VI or a VF or a D or a T? Okay, I think I'm in forces, especially because I see a Newtons. So this is a job for a free body diagram. Jaden, represent the mass with a dot. Jaden, my friend, what are the forces acting on this mass? Get the obvious one. Good. What else? Yep, which way? Yep. Bigger, smaller, or the same size as mg? Uh-oh. I don't know. Or
I know.
do I?
Do I know?
How do you know?
Look at the top part.
Do I know the mass?
Yeah.
Get your calculator out, please. All of you, including Jaden, quickly crunch mg on your calculator. 12 times 9.8. What is it?
It's 117.6.
Okay, so how big is gravity, Jaden? On your calculator, you just told me. No. mg, right?
Oh.
12 times 9.8, what'd you get? How big is gravity? How big is tension? Who's winning?
Gravity.
Has to be. So draw tension shorter, exaggerated. See how we worked our way out of that one? Okay. You'll always, if you know the mass, you can always find mg. Jaden, who's winning? Who's losing? What does winner minus loser always equal? Yep. Use Alex's theorem to get the A by itself. How to get the A by itself? How to move the M over? Is the M subtracting from the A?
Oh, no, fine.
Okay, so all of you can, if you want to on this line, look up. You can cross out the M, big fraction bar, and tuck it there. Here's yet another equation for A. Are you starting to see why I didn't bother trying to give you every possible equation on your green sheet? We're going to derive it from scratch using F equals MA, winner minus loser equals MA. So you ready? Let's plug and chug. A equals Jaden. What's M?
What? 12.
Jaden, what's M?
Well,
What's G? You know this. Nope, that's the force of gravity. Yes. Minus, what's tension? They told me, go find it. Yep. All over, what was M?
12.
12. Is this a fraction? Yes. Is there more than one thing on the top? You'll either need to put brackets around the top or use your fancy schmancy fraction button. This one I can't do in my head. Oh, built-in error check. What are we trying to find? Acceleration. If I cut the rope, what's the maximum the acceleration could be if we were in free fall? I have to get an answer less than 9.8 because tension's slowing it down. So there's a bit of a built-in error check for these tension questions. If you're finding an acceleration, it's going to be less than 9.8. Did you all get 1.63?
No. I got 1.9. Oh, I need brackets.
I got 8.98.
I'm silly.
And it's an acceleration, meters per second squared. Don't clear your did you clear your calculator?
I did.
Okay.
I did. You have to use brackets, you silly.
I don't have to use brackets.
Or your fraction button.
I have my fraction button.
But you don't know how to use your fraction button.
You don't know how to use it.
Okay.
Equation in 20 different steps.
Yeah.
Wow.
Almost done.
I got it.
Okay. Example 10. Turn the page. Mr. Dewick jumps out of an airplane. Imagine he jumped out of an airplane. Once he pulls his parachute, air drag has a force of 1,250 newtons. What's his acceleration? What's this question asking me to find, Nick? Did they give me a VI, a VF, a D, or a T? No. Do you see a force in newtons? I'm going to find acceleration using Newton's laws, using forces. This is a job for a free body diagram. How do I know that? Because in this question, there's more than one force. There's air resistance, air drag, and the obvious one. What's the obvious force? Gravity. So here's my free body diagram. Nick, what were the forces acting on me? Get the obvious one. Okay. What else? Air drag. We'll call it, how about FD for drag? Bigger, smaller, or the same size as mg? I don't know. Or do I?
Yes.
Calculate mg on your calculator really quickly. 92 times... Wait. I'm lazy. Instead of 9.8, what's a nice round number really? I could probably just go 92 times 10. What is 92 times 10? It's going to be less than air drag. Okay, so if you're looking for a cheap hack and you're lazy, times it by 10. Unless it's really close to the force they gave you, you'll be okay. So air drag is bigger.
So big.
I always exaggerate it so that I don't forget. Okay? Nick, who's winning? There's no U in that equation there. There's no Dewick in that equation there. There are two forces, mg and FD. Who's winning? Drag. Who's losing? What's that going to equal? MA. By the way, which way am I accelerating right now? What direction?
You're going up.
How does that work?
Because air is pushing up on you.
First of all, and this goes back to Ronan's question earlier, which way am I traveling? Down. Am I speeding up or slowing down when I pull a parachute?
Slowing down.
If I'm traveling down but slowing down, which way am I accelerating?
Upwards.
All Newton's laws, Ronan, tell us is the direction of acceleration. They tell us nothing about the direction of velocity. That's why it's so tricky. Don't kid yourself. This is tough stuff. I've seen questions where physics teachers have got some of these wrong. What am I trying to find, Nick? How would I get the A by itself? Oh, Alex's theorem. Okay.
Oh. Thank you, Alex.
How big is FD, F drag? Yep. Do I need to multiply that by any? No, it's newtons. I don't need to multiply it by an acceleration. That's newtons. Minus, what's M? 92. What's G? 9.8. Don't need to put the negative in. I took care of that with my winner minus loser. Divided by. What do you get? Try this one, please.
Y is 1,254 and 92 times 10.
It's FD minus MG equals M.
That's
My-
what I have as well, but isn't FD 92 point?
No, that's a mass. FD is air drag, right? It tells me air drag has a force of 1,250.
And FG is
Gravity.
Ah,
What's the M? Oh, so you're doing M equals 92. Ah, I see. Gotcha. Well, hey, that's not fade in also.
Did you all get 3.79?
yeah.
Okay.
Divided by M.
But by the way, just under nerd trivia, as I slow down, this parachute is slowing me down. As I slow down, air drag gets smaller and smaller until eventually it exactly matches gravity and I stop accelerating, and that's my new terminal velocity. But the parachute gives me a terminal velocity that's survivable. That's just a bit about the physics of skydiving. Example 11. Caleb jumps from a 19.5 meter high cliff into a lake. If we assume his mass is 65 kilograms, okay. Manav, what's A want me to find? Oh. Okay, now I think I'm going to be deficking and listing my data. Oh, what's VI if we're cliff jumping?
0.
0. What's A if we're cliff jumping? And now we will bring in the negative because last unit we did have to be fussy with down being negative. Here, this unit, it's easier to let the winner be positive, and you'll see why as we get into more and more complicated questions.
Yeah.
What else do I know? Thank you. Oh, I was going to jump and say it can't be 19.5. Negative 19.5. Which equation? Liam.
Oh, you're so good.
Get the t by itself. I'm going to go like this. Divide by 0.5a square root. There was one of you who did this on the test, but each time forgot to type their square root button. They wrote it, but they didn't type it. I won't mention which one of you it was, but on every single question, they forgot to hit the square root button. Just saying.
What was it?
So, throwing away silly mistake marks, right?
Oh,
It's going to be negative 19.5. 0.5. It's going to be almost exactly, I think, 1 second.
gosh darn.
I got to put brackets around the bottom of my fraction since Liam used the 0.5 version. Sorry, almost exactly 2 seconds. I said almost exactly 1. Almost exactly 2 seconds. Because it almost works out to 4 in there. Is that right? 1.99? Okay. What does B want me to find? Which is what? Okay, it wants me to find VF. You know what? Let's use our answer from A. I'm going to be lazy. I'm going to go VF equals AT.
Yeah, why would you do that?
It's not even that much faster.
Yeah.
Because I have that on my calculator as an answer button.
Yeah, I'm already done it.
And did you remember to put in the negative, doing it the other way?
Yes, I did.
You just made a mess.
Yes, I did.
Wait, no, he did it on his calculator. Wow. Ronan, you're
Okay.
a machine.
Yeah, you can go whoop. Come on. You can go 0 squared minus, or sorry, yeah, no. I want to go VF by itself, Mr. Duick. 2 times negative 9.8 times negative 19.5 square root. And the only tricky part with this, I have to remember to add the negative. Okay? That's all review. We haven't used winner minus loser forces yet. Okay. Camille, what C you want me to find? Ooh, am I going to use forces here? Wait a minute. I noticed they also gave me a displacement. I think I'm still last unit, and I'm doing this so you can figure out how I know when do I use free body diagram and forces and when do I fall back on kinematics. So I'm going to make a little note here, A equals question mark. If his feet just barely touch the bottom, what's his final velocity at the bottom? What am I trying to hint at? I think I'm trying to tell you that Caleb came to a stop, just barely touched the bottom. So let's say he came to a stop. D is 2.5. Do I need to make that negative? He is ending up below from where he started. Yeah, okay.
That's a jump. It's like, because what did he hit the water at 7 kilometers an hour? So, is that
If you tuck, you're okay. Yeah, if you tuck. A 19.5 meter high. Remember, we saw the world record, and that was 59 meters high. 19.5. Now, if you land wrong, you can absolutely injure yourself. 19.5 meters, about 6 stories. So you're high. Okay. I need one more thing. Yeah. VI is negative 19.5 because how fast he was traveling when he began to stop in the water is how fast he was traveling at the end of his free fall when he hit the water. Nice. Camille, which equation? Get the A by itself, please. Is that right? VF squared minus VI squared all over 2D. So 0 squared minus negative 19.5. I'll be with you in a second, Spencer. Squared. Sorry? Oh, okay. Now here, because we've let down be negative, which way is he moving in the water? Is he speeding up or slowing down in the water? What direction is he accelerating in the water then? We're going to get a positive answer because you decided to let down be negative. Or you could have let down be positive and we would have got a negative answer slowing down. I'd take either of them. It all depends on what you decided your reference frame was. Okay? And this is why I'm kind of fussy with direction, but also not, because it all depends, Alex, which way you decided to let be positive. I'm positive. 0 squared minus 9. Oh, I'm going to use my answer button. I didn't bother including the negative because I knew I was going to square the negative anyways, so I just included the subtraction sign but not the negative because I'm lazy that way. Dope. Typo. Did you get 76.4? So about 7.5 G's. Again, doable. I used my answer button the whole way through. If you used the 19.5 and not your answer button, that third sig fig will be different. Yeah. 2 sig figs we should always match. Third sig fig if you're not using your answer button. But hey, start using your answer button. Do yourself a favor. Okay. So that's about 7.5 G's. Going back to Parker's question. No, yeah, Parker's question. Survivable as long as you tuck and you're careful and you're in good shape. Yeah. D. D. Okay. Liam, what's D you want me to find? The net force, and I put the word net on purpose. I don't need to do a free body diagram. If you look on your green sheet, the equation I gave you said F net equals MA. If you ever see net force, you can go straight to MA. It means I've done the winner minus loser already. Did they give me the mass in this question, Liam? Go hunt for it. It's there somewhere. Was it 65? I probably gave it on the first line usually. Yeah. And the acceleration, hey, that's our answer from part C, which was 76.4. Again, I'm going to use my answer button. I have 76.44. So 65 times answer button. The force that the water exerted on him, just shy of 5,000 newtons. 4,968.6. Now to put that in perspective, getting hit by a baseball bat is around 6,000 newtons. And going back again to Parker's question, this is doable if you're in good shape, if you tuck right, if you absorb this carefully, but this is not, ooh, I want to do this casually. I agree. So I'm glad you noticed we were getting some big numbers. I'm going to write 4,970 newtons. What's what?
65.
M. I gave you the mass in kilograms somewhere.
Yeah.
Right? Okay.
Assuming his mass.
Example 12. So that question was purely designed to give you an idea, hey, when do I use last unit stuff for acceleration? When do I use forces for acceleration? Example 12. Draw a free body diagram for a cyclist moving to the right at a constant speed while pedaling. Okay.
Constant speed.
Oh, thank you for noticing. Let's underline that. That's the key to this question.
Yeah, it is.
What are the forces acting on this cyclist? Get the obvious one.
9.8 gravity.
I got to be fussy. 9.8 is the acceleration, not the force. mg, mass times acceleration, that's the force. And so I'll jump on you a little bit if you tell me, oh, gravity is 9.8. The acceleration is 9.8, but the force,
I don't have his mass.
it's okay. But we're going to label a free body diagram with forces. Is the cyclist sinking into the ground like quicksand?
No.
Are they flying like Superman?
No.
So I know there has to be an arrow same length pointing up, and that is the ground pushing up. By the way, that's why when you're on mud, you sink, because the mud can't match gravity. You'll sink until you hit firm ground. The firm ground can match gravity. Okay? Again, kind of Captain Obvious, but that's why you sink in mud. What else?
Wow.
What else?
Whoa.
Well,
Then they have to be balanced.
so where else must there be an arrow pointing?
Oh, the other way.
Water.
What force is that?
Air resistance.
Yes. Okay, so let's suppose this is the hardest, that arrow should be the same length. Let me eyeball it a bit better. So let's suppose you're pedaling as hard as you can. How can you go faster? Hang on, I'll take your question.
You did the thing cyclists do.
We've just explained why the Tour de France riders take that pose. They've maximized how hard they can pedal, but they can still control their air resistance. Drop that down, and you'll have a bit of an unbalanced force. You'll accelerate a bit more to a new constant speed, a higher constant speed. And again, kind of Captain Obvious, maybe if you've done any cycling, but there's the physics of why.
That's why
Okay.
planes are shaped like that.
If they're the same speed, you wouldn't be moving.
You absolutely would be moving forward. Don't confuse motion with acceleration. You won't be accelerating forward. Newton's first says you're going to keep going in a straight line at a steady speed, just like outer space. Now, in outer space, there's no forces. Here, the forces are balanced. But in both of those situations, the net force is zero. This is why Newton's first is such a powerful tool. But it's also tricky to wrap your brain around.
That's how Michael Phelps.
Okay? We're nearly done. Draw a free body diagram for an inline skater who's dragging the toe of one skate in order to slow down and stop. Okay. What are the forces acting on the skater? Get the obvious one. Which way?
Gravity. MP down. Because we have to use forces,
Okay.
not accelerations.
Are they sinking into the ground like quicksand?
No, but they're also not flying up into the air like Superman. I like this question.
Okay. What else?
They're going.
Let's imagine they're traveling to the right.
Okay.
In this question, are they speeding up or slowing down?
Okay.
So if they're traveling to the right but slowing down, here's the key. What direction are they accelerating?
To the left.
Which way must there be an unbalanced force pointing?
Left.
To the left, to the left, to the left, right, left, now,
That's their dragging toe.
left, right.
What else?
And then for the right, you have to put speed. Speed that you're going at.
Why would you put velocity on a force diagram? Okay? And this is good. Matt, I'm glad you said that. We have to really be meticulous. Okay? So I'm not putting velocity on a force diagram, so no. What else?
The ice.
This is an inline skater.
Force of
Oh, yeah.
Even skate.
Okay. I'll give you a hint. It's a trick question.
You don't put anything.
There's no force pointing forwards. This is enough for a skater to come to a stop. Look, will that bring them to a stop?
Yeah.
There is nothing pushing them forwards. There's only a force pushing them, pulling them to a stop.
That's assuming this.
Again, this is because it's so easy to confuse motion with acceleration. Newton's laws don't tell us which way you're moving. They only tell us which way you're accelerating. I like this question. I like this question. I like this question.
I called it.
That's when object in motion stays in.
That's Newton's first. Yeah.
And a person in bed stays in.
Hey, what's the free body diagram for a car hitting the brakes and slowing down? Okay. What?
Same thing.
Parker, what was that?
It's the same thing. There's nothing pushing forward.
We would have gravity down, bigger force of gravity.
Dragon.
Ground pushing up, bigger force of ground pushing up to keep the car from sinking in. We're slowing down. This would be, we'll call it
Brakes.
brakes. And you're right, there is nothing pointing forwards. That's the force of a car slowing down. That's the force when you're squeezing the brakes on your bike to slow down. That's the free body diagram. When you're dragging your foot to come to a stop, if you're rollerblading, that's the free body diagram. If you're snow plowing skis to come to a stop, that's the free body diagram. The force would be a different title, but I'm telling you, gravity down, ground, or snow up, and there's an unbalanced force bringing you to a stop. There is no force pushing you forwards. You may be moving forwards, but Newton's laws don't tell us motion. They tell us acceleration. Take a look at number one.
That is gravity.
You're going to want to do these on a separate piece of paper. I'm going to do 1A with you here in the side, just so you can kind of see how this is looking, and then you'll try the rest. So a rope is attached to a 2 kilogram rock, so M is 2. It says draw a free body diagram and find the chord tension if. So for part I, what are the forces acting on this rock? Get the obvious one.
Gravity.
In part I, which way are we accelerating? Up. That's why the big up is there. Which way must there be a bigger arrow pointing? What force is that? It's the rope. But what name have we given to the force from a rope? Tension.
And John.
Who's winning?
Tension.
Who's losing?
Gravity.
Equals MA. And it wants you to get the tension by itself. I'll let you try and figure that out. You'll do a separate free body diagram for each one of these. Do a real quick sketch. See if you can generate the equation, and you're going to get the T by itself for number one. Okay? We did an example of each one of these if you look at the rock tension questions as well. Number two, what does 2 part I want me to find?
What's the weight of a 5?
What do I mean by weight? Isn't the weight 5 kilograms?
Yeah. No, it's not mass. It's the mass.
How do I find weight?
You gotta do.
It's on your green sheet.
Winner loser.
It's on your green sheet.
You gotta do weight equals FG equals mg.
So
Force.
5 times 9.8, that's the weight.
Mass.
Number 2 is the same as number 1, but in number 1, I was giving you the acceleration and saying find the tension. In number 2, I'm giving you the tension and say find the acceleration. Alex, how will we get the A by itself? We'll use Alex's theorem. You'll end up dividing by the M. You'll do a free body diagram. You'll have to figure out who's winning. Well, wait a minute. What's the force of gravity in this question? What's tension in part A? Who's winning? Who's winning? Okay? So, your homework. Number 1. Number 2. 4 is good. 5 is good. 6 is good. 7 is good. I think I'm going to assign all of them.
I like number 7.
8 is good. 9 is tricky. Although I'm going to tell you that 9 is all physics 11. You can do A, B, and C without free body diagrams using kinematics, but you need a free body diagram to find the force from the rope. What's another name for the force from a rope? To find tension. Okay? I'll talk about D next class if I need to. 10 is good. 11 is good. Can you all look at number 11, please? There's a weird glitch when I print this. Do you have for number 11 4 different small diagrams?
No.
Yeah.
Yes? So I don't know why. Mine always just prints one big diagram, but you have the 4 small diagrams? Yes? Okay. And the answers didn't get covered up? The answers are all there? Okay. Okay, so number 11. 12 is good. 13 is good. 14 is good. Before, you're going to have the rest of class to work on this, so almost 2 hours. But before I turn you loose, put your pencils down, look up.
Oh, we're watching the video. Yeah. No, it's not called that.
So the question we want to ask is, or answer is, why does the Earth spin? It's a good question.
So I'm down in West Vancouver, British Columbia,
Hey, West Van.
which is where I grew up. And at the local beach, there is this 2.5-ton granite sphere that was made to have a tolerance of 0.02 of a millimeter. This is an amazing granite sphere, and it's floated on a thin layer of water.
Any of you seen that? It's by West Van. There's also one in Disneyland in Tomorrowland. They've got it floating on a very, very thin sheen of water. And in fact, this granite sphere has a tiny map of the Earth on it, or a tiny, full-size map of the Earth, very finely etched on it, okay? It's floating on a very, very thin sheen of water, which means it's nearly frictionless, okay? Yeah,
Someone ever like pushed it off?
you can't. It's got enough mass, there's no way you're moving it off, okay? So, what can we learn from this?
And it just presents an amazing opportunity to study inertia. And that's why I'm down here, to have a chat with some of the people going by about why the globe spins, and in fact, why the Earth spins. Why does the Earth spin? Why does it turn like that? I think it's...
So here's the first, for you folks. Why is the Earth spinning?
It doesn't want to move. It's staying the same place.
Parker, what was that?
Newton's first. If it's at rest, it wants to stay.
Objects in motion stay in motion.
No, they're both. That's both part of it. Okay. Huh. Let's see.
The gravity, for it to keep us down on the ground. Is that right?
Does gravity make the Earth spin?
How does that cause the Earth to spin?
Again, my basic science fails. It's failed. Gravity, he guesses, looking...
Gravity. Oh, yeah, gravity.
Do you think gravity is what makes the Earth spin?
No.
Okay. But I'm trying to tell you, Newton's laws are very difficult to wrap your brain around. In fact, I guarantee that in grade 12, I'll get, any of you that take physics 12, I'll get you all with a puzzle, and you'll go, oh, I should have spotted that. But it fooled me, it fooled a room of physicists. People really wrestle with this. So gravity does not cause the Earth to spin.
It's not stopping. Would you agree with me?
Yeah.
So why is that?
some sort of force that's,
You think there's a force down there pushing it?
yeah. I'm gonna go because the upthrust from the water is probably angled in such a way that it's, because it's a spherical shape, it's probably pushing on it at an angle, so it spins constantly.
Yes. What is the centrifugal force that keeps it going? What is that force? And where does that force come from?
Is there a force that keeps it going? Is there a force pushing it around?
Within the Earth's core? Is there not something that drives and dictates said centrifugal force?
No, there's no force that's making the Earth spin.
Just because there's no friction, that's just going to keep moving and moving.
Parker, I'm gonna come back to you in a second. Hey.
This is the law of inertia, isn't it?
Oh! Yeah, he's so smart.
What's the law of inertia?
Every action causes equal and opposite reaction.
His name's Isaac for sure.
That's not the law of inertia. That's Newton's third, he just said. He said every action, he said forces come in pairs. That's not the law of inertia. The law of inertia is the one that says if forces are balanced, A is 0.
If the force of inertia maintains this,
But inertia, which is a great idea, is not a force.
Right? Inertia is not measured. What is inertia?
It's a concept.
how would you define it?
It's just the tendency of all objects with mass to maintain their state of motion.
And we're going to treat inertia and mass as the same thing, except when we get to Einstein, you'll find out that when you get near the speed of light, they're not the same thing, but we're not going near the speed of light.
Okay.
So if they're stationary, they want to stay stationary. And if we anthropomorphize them.
Yes, and if they're moving, said anthropomorphized objects want to keep.
Basically, whatever motion they have, they like to continue in that state of motion.
Yes.
The Earth does that without any forces. This does that without any forces.
Yes.
Yeah.
Parker, you're the first student in about 15 years who, when I posed the question, right away said, it's obvious. It's inertia. The Earth was spinning when it started and it hasn't stopped. The Earth was formed out of dust that was spinning, and there was nothing to slow that spinning motion down. It's going to keep spinning. Now, there is something. What is slowing the Earth down? Yeah, the moon. Eventually, a few billion years from now, in the same way that the moon always points the same face to the Earth will be pointing the same face to the moon a few billion years from now. Okay. Well, it'll give you, if you're on the moon side of the Earth, a spectacular nighttime view.
That's assuming the sun will flow.
Yeah, it's the sun is right on the threshold of either blowing up or just becoming a stable red giant, and how big it becomes. It's right on the border of whether Earth will get swallowed up by that or be just outside and get fried up by that. It just happens to be that kind of a number. Okay? Okay. Let's keep going. Part 2.
Well, you're...
Because that granite globe has a lot of inertia, a lot of mass, it is tough to get it to accelerate. Even though it's nearly frictionless, it's sitting on that very thin film of water.
If I apply a force to the globe, I can actually get it spinning in roughly the same way that the Earth spins. But it is tricky. There's very little friction on the bottom because of it being supported on this thin layer of water. And you can see the more force I apply to it, the more it accelerates.
Yeah, that works, because F equals what?
MA.
Bigger force, bigger accelerate, because the mass didn't change, so the acceleration must be getting bigger.
Ooh, so we're getting it speeding up here. When you push that, like, it's not too easy to get it going. Why is that?
Friction, probably.
So strange. Why is it not really easy to push? What is it about this giant sphere that makes it a challenge to push?
The weight.
What's weight? And now you've learned, when I say weight, what are we talking about? It's measured in newtons.
Gravity.
Look at your, what?
Gravity.
Force of gravity is the same, that's a synonym for the word weight. It's not the force of gravity that's making this tough to push.
The resistance.
But
The
we're not trying
gravity.
It's really heavy too, so I'm pretty sure the weight of it sitting down is making it tough too.
You don't think its weight is supported by that water?
Well, I know it's supported, but
Ooh, free body diagram. What are the forces acting on this? Get the obvious one. Is it sinking through the cement? Like, is it flying up? So the water must be exactly canceling out, the force, upthrust force from the water must be canceling out the force of gravity, which means not going to accelerate in that direction.
even though it's supported down, moving it, it's still, like if its center of gravity's here, we still have to push the weight coming out from here. So it's pretty heavy, I'm pretty sure.
They're mixing up weight with inertia, mass, right?
Most people will say if you just apply a force to it, it starts moving. That's not really the point I want to make. The point I want to make is the more force you apply to it, the more it speeds up. The more it gets going faster and faster and faster. But it's got 2.5 tons of inertia, so you can really feel that you have to push hard to accelerate it. What do you feel when you push on it?
Just moves. When you push something, it moves.
Does it do something more than move?
Spinning,
It's...
rotation, velocity, speed. There's some.
What word are we looking for if you apply an unbalanced? And again, you can see confusing velocity and acceleration. Ronan, it's easy to do. It's so easy to do. It happens all the time. And I'll keep throwing puzzles like that at you during this unit to force you to really separate the two, and I'll do it in Physics 12 as well.
Some word you're looking for.
There is a word I'm looking for. What do you feel? Is that hard?
Not really.
It's easy? It's
Well-
not going very fast, though.
It's not like hard to push, but it's sort of hard to get home fast.
It's too big to make it fast.
Is it hard to make it fast?
Yeah.
Why is it hard to make it fast? Can we try?
Yeah.
Let's try it. Let's get it going really fast. Yeah.
She says the exact thing you're looking for.
What is that? Rotating.
Oh,
Spinning.
so close.
Moving.
How do you make it go faster?
You only need to push hard, and more harder than that.
Yeah.
Without the proper vocabulary, that kid said you need to apply a bigger force to make it accelerate more.
He's smart.
Right.
That was a
You put a force on an object, a net force, an unbalanced force, and it...
If you have an unbalanced force, an object will accelerate.
Come on.
Goes.
Going. He leaves scientific whatever. It goes. You study physics, right?
Yeah. Which means I'm probably looking a little bit like a moron here.
No, you're
but
not
that's
looking-
okay.
No, I've done this with many students that have had physics before. This is tough to wrap your brain around. So if you're finding this tricky, you're normal. Remember, I told you Isaac Newton overturned 2,000 years of science. For 2,000 years, scientists couldn't wrap their brain around this. This is not easy.
Not at all.
It's easy to push, but like if you try to go fast, then it just sort of stays the same speed.
But could you bring it to a stop?
Probably not. Definitely not.
Can you give it a shot?
You stop the water.
Well, other than cheating, yeah.
What do you think?
Not gonna happen.
Come on,
I
come on.
can't.
Which back into it? You can do it. Ah.
I don't think it's gonna work, but we can give it a shot. Kinda.
What do you see there?
It's stopped, but it's only stopped because it's on like a very soft thing of water.
Does it need to be on a soft, or objects at rest will, if there's no unbalanced force, stopped will stay stopped, moving will stay moving. That's all Newton's first tells us. Tells us nothing about how it's going to move.
Pretty much, I'm pretty sure.
So it's not going to stay stopped or what?
It shouldn't.
Because once they take their hands off the thing, the water will make them bounce.
Alright.
Are you applying a force to this sphere here?
Yes.
And what happens when you apply a force to the sphere?
Then it changes
Ooh.
like speed.
If you apply a force, it changes speed. What do we call it? Okay, it's not using the physics word, but that's good.
That's a pretty awesome observation you just made.
Yeah,
Do you know that?
I guess.
So we could generalize. We could say force causes
Change.
In?
Speed.
Force causes change in speed. What's a fancy word for change in speed? Now, we would add, and also change in direction, because vectors, but there, that kid just picked it up.
Man, you were nailing this. Can you give me a high five? Boom. What do you think physics is?
Like how things work, I guess.
And you want to know how things work?
Yeah.
How old are you?
11.
You seem pretty smart for being 11.
Okay.
Do people tell you that you're smart?
No.
You think you're smart?
No.
I think you're smart.
Okay.
You take my word for it?
Okay.
Really?
Yeah, I guess.
That kid picked it up.
Think you're smart? No. Do you have any